And we are your 2021 Honolulu Nerd Nite co-bosses. With me tonight are Marissa and Helen, and I am Tony. And with me, you may hear him in the background, is my boss. There's no co about it. He's just my boss, my son Jojo. We'll be running the show for you tonight, and we're very excited to have you with us this evening. A couple of quick ground rules. Please, if you can, save your questions until the end of each talk. You can go ahead and type them into the chat at any time, but we'll come around to them at the end. One of us will be watching the chat throughout to take note of questions so that we can come back to them after the talks are over. Any kind of disruptive, respectful, any kind of behavior that's generally uncool, and we you out immediately, and you will not be welcome back in. So please, everybody, be respectful, stay cool, and we'll all have a really nice evening. We're going to get started with some warm up and get you guys ready. But first, we have our three speakers for tonight. So first, we're going to hear from Vanessa Almanza about hurricanes. And then Sadie Blancaflor is going to tell us about climate displacement, people who are going to be forced to leave their homes as a result of climate change. And then we'll also hear a little bit about tsunamis at the last talk with Nathan Becker. So to get things started off, just a quick couple things that happened in the last few months while we were away, since we did not have a June talk. There was a study recently published on dumpster diving cockatoos from the Max Planck Institute of Animal Behavior. So this is a bunch of different cockatoos that were observed throughout different suburbs in Sydney, down in Australia. And different Sydney neighborhoods, cockatoos are using different methods to open garbage cans. So one of the big takeaways from the researchers of this study was that it's some evidence that different cultures are evolving within a parrot species for the first time, or has been observed. I shouldn't say evolving, but has been observed in parrot species for the first time. So they started with 1,300 citizen science responding to surveys in 2018 and 2019. Before 2018, the behavior had only been reported in about 3 different neighborhoods. By late 2019, the observed behavior was occurring in 44 out of the 500 neighborhoods in the survey. A clear pattern was observed, started in the original 3 neighborhoods, and then as we moved out away from those, there was less and less incidence of it. So it seems to have spread that way. The further out you got, the fewer observances there were. And according to the authors, the pattern suggests that the birds were learning from each other and spreading their behavior through the city. There was one distant neighborhood where the behavior was observed that did not have a geographical connection to the other cities or the other parts of the city. And so it seemed to have kind of popped up on its own, or potentially a bird flew further than they would have thought they might have flown to spread this behavior. Researchers then caught and tagged and filmed 486 of these dumpster diving birds. They noticed several common steps within all of those video observations. First, opening slightly at the front corner and moving towards the back, and then flipping the lid open once they moved towards the back. So over all of those different observations, those ones were some common patterns that emerged. There was some variation in the use of the bill, just the bill and the foot, where they were holding the lid, etc. And the further apart the birds were geographically, the more the technique differed. The researchers claim that this indicates social learning, and not just that you can open a lid of garbage, but exactly how to open it, because those behaviors were varying from neighborhood to neighborhood. Different calls by parrots have been known to have be regional and have dialects. That's been documented, but this is the first time that a foraging activity has been shown to have a regional association as well. So that's dumpster diving cockatoos. The next thing I wanted to mention is that the Hubble Space Telescope is not dead yet. The 30-year-old telescope, if you didn't hear, had some issues back in June. The payload computer stopped working, which is not too unsurprising because the computer was designed in the 1980s. Although the hardware was replaced in the last astronaut servicing mission back in 2009, that's still quite a long time ago, and those computer systems are just old. They were designed with redundant systems though, and so they were able to switch to the backup power control unit and backup command unit in Science Data Formatter. And then they ran some tests to make sure that everything was working properly. And then they were able to make their observations again. As of July 17th, the science instruments were back to operating normally. And it's important for Hubble to continue operating because it's been one of the most important tools that astronomers and astrophysicists have had since its launch in 1990. Over 1.5 million observations and over 18,000 scientific different papers have been published with data from Hubble. Some of the most significant discoveries that have been made in the last 30 years have come with Hubble data, including the accelerating expansion of the universe, evolving galaxies over time, as well as the first atmospheric studies of planets outside of our own solar system. NASA expects Hubble to continue working for many more years and working with the new telescopes like the James Webb Space Telescope, which will be launching a lot later this year. So that'll be a cool one to look for. It's going to do a lot of things that Hubble can do as well, but even then some, and it's going to be even further away from the Earth actually so far that they won't be able to go and visit it out in its orbit once they put it there, as opposed to Hubble, which is in a little bit closer to Earth, so they were able to go and do things like replace the primary mirror that got put in backward, or the lens that got put in backwards when it was first launched. So this is not the first issue that's come up with Hubble. I also wanted to use this as an opportunity just to share some pretty pictures from Hubble. So this is one called the Hubble Ultra Deep Field. So all of those little colorful smudges are different galaxies, except for this thing here. This is a star that is within our own galaxy, just within the foreground of that part of the image. So this is several different exposures taken from 2003 to 2012. And then they get all put together, and then they're highly processed to be able to show the data visually like this. This is NGC 6380, which I looked it up and it doesn't really have a nice sort of common name, but NGC is the new general catalog. So it's a way that astronomers are able to, they kind of keep track of different objects like this. So this is something called a globular cluster, which is a group of stars that is very, very old. Some globular clusters are almost as old as the entire universe, about 13 billion to 14 billion years old. And all of these stars are very strongly tied together gravitationally, and so they don't drift apart very much, which is something that we see in an open cluster, which is also a group of stars together, but with less gravitationally bound. So this one specifically is about 35,000 light years from Earth in the constellation Scorpius, which is also the Scorpion, or known here in Hawaii as Maui's fishhook, Kamakanui o Maui. And then finally, one of my favorite objects in the universe that we have images of, this is something called the Veil Nebula. And it's an emission nebula, which means that radiation from all of the stars essentially ionizes the different gases that are out there that we see as these different colored filaments like this. Images like this one and this one in particular have been very highly processed after the observation is taken with the telescope. So there's 5 different filters that were initially used on this. All of that data comes back to scientists, and then they're able to, if it's not something taken within the visible spectrum of light that we see, if it's an ultraviolet, or if it's in radio waves, or if it's in infrared, like all of those different wavelengths can be assigned a visual color, and then we're able to see it. So this particular image is a kind of retake of one that was already existing, but we're able to see more of those filaments in a bit more detail than before. So we want to also know what makes you nerd out. We want you to come and be a speaker for a future Nerd Night. For the rest of this year, we will be doing more virtual, and then we'll kind of see how things progress with the pandemic. We were starting to feel a little bit better about doing in-person events in 2022. I don't know about now, things are not going really well, so we'll just have to keep an eye on that. Speaking of which, just my public health plug, if you haven't been vaccinated, please go and get vaccinated. It is safe, it's effective, and it's one of the best things that you can do to help your community, and we can all get through this. But we do want to have you come and be a presenter for Nerd Night. So you can contact us through our social media, through our email. We'll put those slides up in between the different talks. And hopefully you can come and join us for another talk later this year or next year. We want to give a huge shout out and mahalo to DJ Globe. He'll be spinning some music for us during our intermissions between talks. And of course, a big mahalo to all of you for joining us tonight. So we're going to get things started here in just 1 second. So grab your drinks, grab your food, whatever you got, and let's get started. So we're going to roll right into our first talk. So I'm going to stop my screen sharing and we'll turn it over to Vanessa Almanza. So please help me welcome Vanessa.
Woo! Vanessa, you're muted. Just letting you know. Yep, there you go.
All right, so thanks guys for coming tonight. My name is Vanessa Almanza again. I'm a meteorologist with the National Weather Service here in Honolulu, and it's also co-located with the Central Pacific Hurricane Center, and I'm here to talk to you guys about hurricanes. So what is a hurricane? And no, I'm not talking about them tasty treats from New Orleans. Talking about those weather systems that come to Hawaii every once in a while. Essentially, the textbook answer of a hurricane is that it's a warm core, non-frontal. So basically, there's no cold air colliding with warm air mass. It's just all warm, moist air with deep convection around a closed circulation, and originates in the subtropic regions. In this satellite image, we have a few examples of different hurricanes in different stages of development, from tropical depression to all the way full-blown hurricane. So the general term that we call them is tropical cyclones. So in forecasting, we do a lot of ingredients-based forecasting. So to make a hurricane, you need a low wind shear, you need a moist, unstable atmosphere, you need 2 parts of warm water that's at least 80 proof, 80 degrees Fahrenheit, and the little splash of low-level disturbance, and all of this needs to happen about 5 degrees away from the equator. Hurricanes are the San Francisco scale hurricane wind scale kind of defines the different classes of hurricanes. So you have the tropical storms, which are generally 39 to 73 miles an hour, all the way to category 5 hurricanes, which are greater than 157 miles per hour. A fun little fact is that this scale was first developed by a structural engineer, Herbert Saphir, and he wanted to basically mimic the Richter scale by creating something that could define hurricanes' destructiveness based on the wind speeds. However, he soon found out that that was very difficult because hurricanes bring multiple threats and hazards, such as flooding rains and storm surges. So he handed it off to Robert Simpson at the National Hurricane Center, and then they kind of developed this scale together. So although it's not a good representation of the total destruction caused by hurricanes, it does give us an idea of the potential impacts that you can have, all the way from very dangerous and produce some damage to catastrophic damage. So the hurricane season in the Central Pacific Basin, which is between 140 west and the dateline, or 180 west or east, however you want to describe it, is essentially June 1st through November 30th. In this graphic I have here, on the x-axis I have January through December, and then on the y is the number of hurricanes. And you can see that the most activity for the Central Pacific Basin is in August. Hey, I think it's August now, right? Some of the things that can influence hurricanes is one of the climate is the El Nino Southern Oscillation. And essentially, basically what it is, you start seeing sea surface temperatures around the equator off the coast of South America start to become warmer than normal or cooler than normal. If it's warmer than normal, it's an El Nino year. If it's cooler than normal, it's a La Nina year. And essentially, it's basically like for hurricane season, it's like having a hype man, where you have some people who like bring the party, or you have those whose job it is to actually cool the party down. And essentially what that means is in El Nino years, we tend to have more hurricanes. In this graphic I have here, from 1970 all the way to 2020, you can see the number of hurricanes per year in the Central Pacific Basin. And the red bars indicate El Nino years, where generally you can see that you have the larger numbers. Where, for example, in 2015, we had the largest number of hurricanes in our history, which was 16 hurricanes that year. And then La Nina tends to be below normal or average, which our average is around 5. But those are just tendencies, right, and guesses. And so currently we are in a ENSO neutral kind of year. So in that, along the equator, in that sweet spot, there's not generally sea surface temperatures are near normal or average. So that, depending on the ENSO cycle, the Climate Prediction Center puts out these Central Pacific season outlooks. And because we're in ENSO neutral, coming off the La Nina and potentially going into another La Nina, they predicted about an 80% chance of near to below normal season this year, with a 20% chance of above normal. And this comes out in like mid-May. And what I like to stress that it doesn't address like the potential impacts that could happen for the island of Hawaii. For example, on the left image here, I have 2017, and the right image is 2020. Both were ENSO neutral years. Both had 2 tropical cyclones enter the Central Pacific Basin area. And 2017 didn't get really close to Hawaii. Last year, one of them got really close. And by really close, here is a radar imagery loop from all 4 of our radars showing Hurricane Douglas just scraping along the northeast of the Hawaiian Islands. And you can see the eye wall structure where there's a big black hole, and you have these red colors swirling around that big black hole, and that is your eye wall of the hurricane. That's where you're going to have the heaviest winds, or the strongest winds, the heaviest rains, and that's what you really don't want to impact the islands. However, even outside of that, you have several rain bands swirling around that, and luckily for us, those rain bands just missed most of the islands, and even the winds, didn't really have anything major happen, fortunately. However, our forecast track error for a 12-hour forecast is about 34 nautical miles. So this could have definitely been a different story, but hindsight's always 20/20, right? So some of the products that we have in this image, this product is probably one of the main products that we produce. It has a lot of information on it. For one, you get the initial position of the a hurricane, you know which center is issuing these hurricanes, and what advisory number it is, as well as the maximum sustained winds. The orange areas show the extent of the tropical storm force winds, and like the darker brown is the extent of the hurricane force winds at that initial time. And then the dots indicate just the X is the initial position, and then the forecast positions are the black dots. And then that can be shown as major hurricane, hurricane, or tropical storm strength, or even post-tropical or potential tropical. And then if it's going to impact land, as in this example, Hurricane Lane was, then the land areas will be lit up with either a hurricane watch or warnings or tropical storm watch or warning. And then the shaded areas just show the forecast track of that center. And notice that the track of the hurricane doesn't include the extent of the effect of that hurricane. So, you know, those tropical storm force winds extend beyond the center, and then that cone of error again gets greater and greater with each day. So day 4 or 5, you have the largest cone of error, where that hurricane center can be 2/3 of the time within that area, and 1/3 of the time it can be outside of that area. So also to touch on that, the hurricane warnings and tropical storm warnings are issued 36 hours in advance of tropical storm force, the onset of tropical storm force winds. However, hurricane warning, we are expecting hurricane force winds eventually after that. And then similar to the tropical storm watch and the hurricane watch, those are just issued a little bit earlier, 48 hours in advance of tropical storm conditions, whereas the hurricane watch is you're expecting hurricane conditions eventually. New this year, and hopefully we'll never have to issue one of these, is the extreme wind warning. This is a short fused warning similar to the tornado warning, where this is our last ditched effort of alerting the public that they need to get into their safe place immediately, because the onset of, because basically the hurricane eye is going to make landfall. And again, this is where you have the strongest winds and the heaviest rains and the most destruction. And so these are just going to be 2 hours long, and then hopefully the hurricane eye would pass within that time. And this will alarm your phones, TVs, or hopefully those things are still working. Some of the other products that we issue, I can give you a little bit more information besides the track of the hurricane and then the wind, is the hurricane threats and impact product. And this will give you an idea of what the storm surge threat is going to be, what the flooding threat is going to be, and the tornado threat is going to be. And then it shows the geographic extent and the level of threat, if it's anywhere between an elevated or an extreme, where you need to take immediate action. So the local office is in charge of issuing hazards that affect the land. And so you'll get all of that information at weather.gov/Hawaii. And on that main page there, you'll see the islands of Hawaii and any current watches, warnings, or advisories that are issued. This is also a point-click map. So if you want to know what's happening in your area, all you have to do is point near where you want to forecast, and then you'll get the 7-day forecast and plus all of the information that's all of the products that we've issued for that zone or area. During hurricanes, if there is a threat to land, we issue a hurricane local summary, and that basically contains all the land-based tropical cyclone watches and warnings, the meteorological overview, hazards and impact information, and some preparedness information. And then we also issue the tropical cyclone VTEC, which is basically an HLS, but it's segmented by the zones. And so getting towards the end, this is where I want to stress the importance of preparedness, because hurricanes are a multi-threat hazard. It's great to prepare for any possible destruction or unfortunate event that may happen, and so early preparation is key. With Lane and even Douglas, we've seen that the shelves get empty pretty quick here, even with COVID. Get your toilet paper in advance and determine your risk. And there's plenty of resources online where you can figure out how to strengthen your home, check up with your insurance, take inventory, and even talk with your neighbors and friends and see what their plan is, and give them some ideas or help them out, and develop an evacuation plan and write things out. Some of the great resources are at weather.gov/hurricanes. There's also local resources at HIEMA. Hawaii Electric has a great booklet on with emergency checklists, great recipes on how to make canned goods taste delicious, and things like that. Another really great resource is the University of Hawaii Sea Grant Homeowner's Handbook. Also has a lot of great information on how to strengthen your home, and they not only talk about hurricane preparedness, but even all of the other hazards that Hawaii faces. And then they have this great graphic on how you can determine if it's safe to shelter in place during a hurricane, or if you need to consider a shelter. If you're considering shelters, know where the shelters are, what you're allowed to take, what you're not allowed to take, who you're allowed to take, and then just be prepared and be safe. So I just want to reiterate that in 2015 we had 16 tropical cyclones. Some of them came close to the Hawaiian Islands, but not as close to last year, where we had a below average kind of year. And like this image just shows that it really only takes one hurricane to really impact the Hawaiian Islands. And so thank you for your time, and I will take any questions at this moment.
Okay, I believe Tony might be preoccupied with his boss right now. So if anyone has any questions, they could go ahead and unmute themselves and ask directly, or if you would like, you could throw it in the chat box and we will read it out for our speakers. I guess I will go ahead and start off with a question because I do have one. So I generally know that this is kind of a thing. I've heard it. I think someone explained it to me many times before, but then the difference between a tsunami or typhoon versus a hurricane, it's just according to the equator, correct?
It's actually according to the dateline. So west of the dateline, or 180 west, is Japan's area, and in Japan they call them typhoons.
Cool, that makes sense.
Yeah.
Can I ask a question?
Sure.
So Hurricane Lane and Hurricane Douglas both kind of like, it looked like they turned or like deflected off, you know, like right at the last minute or something. Is that like a phenomenon, or was that just like a coincidence, or is that like a real thing? Like, is there a reason why they just keep like seem to be turning at the last minute?
It has a lot to do with the steering flow. So whatever's happening in the mid levels where the jet streams are, and for both of them, actually, Hurricane Lane and Douglas were they were getting gosh, now I'm losing my words. They were weakening, and so when they weaken, they're a little bit more influenced by the surroundings, and that steering flow can make them move a little bit more to the north and recurve like that. And that's another one of those complicated forecasting situations that we have, and which makes our forecast error so large, especially with weakening storms and developing storms.
Tuesday evening. Yeah, thank you all so much for joining me. So for a bit of context, I'm a NOAA Hollings intern, and this summer I'm developing this educational curriculum on climate displacement. And I want you guys to imagine this would be projected onto a 3D sphere. And essentially I'm going to be describing sort of the relationship between climate change and forced migration of communities in Alaska and the Pacific Islands. So before we dive in, I have a couple questions for you guys. Where is home for you? Feel free to come off mute or drop it in the chat. New Mexico, interesting. Iowa, wow, we have quite the crew from Anchorage. Riverside, California. Incredible. Okay, so we're from all over the place. New Mexico again. Okay, I need to ask you guys, where in New Mexico? New York. Wow, we're really out here. Okay, my follow-up question to that is, where would you go if you couldn't stay home or go home? Recognizing that's a hard question. What do you mean by stay here, Helen? Like, yeah, what if you couldn't like stay where you currently call home? Like your house in Hawaii. New Zealand. New Zealand is really beautiful. Great mountains. Nowhere. No idea, wherever the wind takes me. Yeah, it's hard to have a question like that. No one really plans for what you do when you can't go home. It's just not something most people think about. Yeah, oh, Katie, but I meant like, where would you go if you couldn't go back to your house or your home or wherever you call home? Okay, your house. I love that. Yeah, I think it is a very hard question. I'm just going to put that out there, but you know, it is hard to have a plan. Sometimes you have to make plans or try and make plans to leave, or you know, try and build infrastructure to stay longer. But it is a hard question to reckon with. It's not something most people have given a lot of thought to. Thanks so much for indulging me on my questions. Yeah, so launching right into it, we're an interconnected planet, and any changes to our environment can have impacts everywhere. And that really makes the issue of global climate change, a global issue, both in terms of its cause and its impact. Climate change is, as many of you know, caused by, this is my reaction to learning about climate change in first grade. But, oh no. And that makes the issue of climate change, climate change is caused by the increasing global greenhouse gas emissions from fossil fuel use. And in many ways, the use of fossil fuels is a lot more prevalent than we realize, from the plastic water bottles that we make to even the way that we get around town in cars or even buses. And all of those fossil fuel emissions make their way into our atmosphere. And this has some pretty severe implications for rising temperatures worldwide, which in turn has impacts on a host of other weather patterns and people around the globe. And something I really want to emphasize in this presentation is that climate change makes conditions more extreme. So, in the context of, extreme weather events, you can have a lot more severe hurricanes, droughts, wildfires. We're really seeing that in California, which is where I go to school. Just really devastating wildfires up and down the West Coast. And they're only getting worse year after year. For many of you, Tony, I know, is at Bishop Museum. If you go on the NOAA sea level tracker, and I can drop that link in the chat, sea level rise is really going to impact a lot of the regions in Hawaii. And the area where Bishop Museum is, if any of you are familiar with that, is extremely vulnerable to the impacts of sea level rise. And if we compare the issue of climate change to moods, for example, it's okay to be sad once in a while, but you wouldn't really want to experience being sad all of the time. And in the same way, a hurricane every so often is manageable for local policymakers in the community to deal with. But hurricanes that are a lot more frequent or really intense will wreak a lot more damage. And it's hard for people to keep living in those areas, so they're forced to move. So that leads me to this slide. In today's presentation, we're going to be examining two vulnerable communities, Alaska and the Pacific Islands. And these two regions are at the coldest and hottest parts of the globe, and they're already at the extremes. And climate change is only going to take them further to the extremes. Communities here are particularly vulnerable.
Sorry, Sadie, just going to interrupt you for a hot second. I don't know if you know, but your slides are in your presentation or the presenter view. If you want to try switching it to the presentation view or kind of go as is, no worries.
I think it's fine as is, but thanks, Helen. Oh no. Can you not see my slides anymore? Okay, there we go. No, okay. Sorry, something just happened.
We can still see your slides.
Can you?
Yes.
Okay. I do not know what happened. Here we go. Can you still see them?
Yeah.
Okay. Or maybe not. Sorry, it's saying that sharing is paused on my end. But that's okay, because we're going to be on this slide for a bit. Yeah, so given that information, what sort of changes do you think we're seeing in Alaska, given that it is up north by the pole? Feel free to drop your answers in the chat or come off mute. I can start us off. My family lives in Alaska, so we're starting to see a lot of melting ice and a lot of melting permafrost. If you go out to Western Alaska, it's having some pretty bad impacts on infrastructure. Any other ideas or thoughts on what sort of issues we might be seeing in terms of climate impacts in Alaska? Cool. Switching gears a bit, this question.
Are
might
you
be-
seeing the answers in the chat? There's a lot of them.
Oh, I am not. Okay, beautiful. Here we go. Oh, coastal erosion. Wow, these are such great answers. Fisheries disappearing. Yeah. Helen said, like, what happened in the Pacific Northwest? Wildfires, heat waves. Gosh, there was just a really bad wildfire in Fairbanks. Permafrost gone, more fires, more weird winters, more polar bears. Yeah. Wet areas getting wetter, hella flooding, but also extreme heat in the interior. Sad polar bears. Yes, very, very sad for polar bears. Everything is melting. Blanching of phytoplankton in oceans. Yes, but that sounds right, but I don't know for sure. Coastal erosion. Yeah, these are such great answers. Okay, perhaps a question that's a lot more relevant to where you guys are in Honolulu, but what sort of changes do you think we're seeing in the Pacific Islands? Drought and flooding, stronger storms, coral loss, more intense weather, mosquitoes spreading. Gosh, hate mosquitoes. Hurricanes, more intense king tides. Yeah, the footage of the king tides is crazy. Yeah, those are all really fantastic answers. Let's take a look. So because of climate change, we know that temperatures are rising, but how out of the ordinary are these temperatures that we're seeing? So this map shows how temperatures compare to the 20th century average. So like that would be our baseline normal. And it shows how out of how much hotter or colder it is from that like baseline. And this map starts in 1964 and continues up to the present. So really watch out for those areas that are getting red or darker red, because it means that those areas are heating up a lot faster. Or sorry, not faster, but they're heating up. They've heated up a lot more compared to the baseline for comparison. So you guys can all see that. So again, this map shows how much hotter and cooler different areas are from this normal, this baseline, starting in 1964, and areas that are darker red have much higher temperatures than normal, and that areas that are darker blue have cooler temperatures than normal. So you guys are all seeing this sphere turn. And yeah, what areas have a lot more red? And what areas have a lot more blue? Where are you guys seeing these really dark red splotches? Polar and inland, poles, north in Australia. Yeah, poles. That permafrost be melting. Yeah, it's rough. Yeah, as you can see here, we're seeing a lot more red, especially around the poles, and a lot more red as we move through time. So not just spatially, but also like in terms of time itself, we're seeing a lot more red because of the impacts of rising temperatures from climate change. And overall, the planet's getting a lot warmer, but certain regions are getting hit a lot harder than others. Global temperatures are rising, and they're only going to continue to rise in the future. Now, we know that these regions are warming really rapidly, but like, what does that actually mean for the people that live here? So this is a map of what regions are the best for human survival. And it's called a human climate niche. And niche means comfortable place and position. And when talking about climate niches, these are the regions with the ideal temperatures and climate for humans to live and thrive in. And the darker areas, red areas, are areas that are unsuitable for humans to live in, while the areas that are dark green are, ideal, a lot better for humans to thrive in. So this is a comparison of the human climate niches in 2020 and in 2070, and like what areas are going to be best for humans to thrive in 50 years. So the darker red areas can refer to like a host of different changes that are happening. Sea level rise means that, coastline areas could be inaccessible. And in most areas, higher temperatures means that crops can't grow. And if you don't have access to food, you're not really going to want to live somewhere. And areas, these red areas could also be subject to really extreme weather events like devastating hurricanes or wildfires more and more often. So if you look at how the map changes between 2020 and 2070, this is over the span of 50 years. Because of climate change in 50 years, some areas will be far less suitable for humans to live in as we currently plan for our current climate instead of designing infrastructure for a future climate. So where do we see a lot darker red colors between these two maps?
I don't see any maps at all.
Oh, you don't?
Your
Yeah, it's
slide
a
just
white
Sadie, we
line.
lost-
Oh, there it is.
now it's back.
Oh, okay. Yeah, what sort of areas are you seeing get a lot redder?
Looks like the Amazon and the whole.
Yeah, it has a big red splotch right in the middle. But I'm also seeing it up towards the north, like all of Canada. Oh, sorry, not all of Canada, but it seems to me like that those areas are getting a lot darker red, and especially like Central America. But anyway, yeah, if you were living in one of these darker red areas, where do you think you would go? To the lighter areas, to the greener areas? Yeah, exactly. And I know this map shows, the difference between 2020 and 2070, but we're already starting to see the impacts of climate change, and people are already having to confront these questions about like, where do they go? So this is an image of Newtok, Alaska, and it's right up on the coast. It's an Alaskan native village, and it's really getting pummeled by climate change. So a lot of the issues that you guys brought up earlier about permafrost and lack of access to resources, this community is really getting hit hard right now. And some of their houses are just crumbling off the side of the cliffs. This is an issue that, a lot of you guys in Pacific Island regions are at least thinking about, is like sea level rise, and where do you go when your houses are flooded and you can't live along the coast anymore. Climate change can also cause drought because of the increased temperatures, and that has pretty significant impacts for, again, like your ability to grow food. And yeah, it's really making people think quite critically about like where home is and where do you go when home won't let you stay. So this is a map of human migration from 2010 to 2015. And on a global scale, we're already seeing migration happening around the world. The purple areas in the map that you see are areas where people are moving away from, while the brown areas are people that are moving to. And also recognizing that this is over a 5-year span, the United States took in 4.5 million people during this time, and we're only going to expect those numbers to go up because of climate change. And this was really shocking to me. According to the Internal Displacement Monitoring Center, around 17 million people were displaced as a result of natural disasters in 2009. And a decade later, that number rose to about 25 million. And if you look at 2020 data, 3 times the number of people that were impacted, I guess a better way to put it, around 10 million people were internally displaced because of conflict and war, and 30 million people were displaced as a result of natural disasters and extreme weather events, which is kind of crazy, right? Whenever we see the news, we always think about people being forced to leave because of war and violence, but in fact, environmental factors are having a really significant impact, and we're going to see that begin to increase, especially as we start to feel more and more of the impacts of rising temperatures. And, on a personal and individual level, even if you aren't forced to move as a result of climate change, it still impacts how you eat, sleep, and breathe. You might not have access to the same foods you like vanilla or chocolate ice cream. I'm a big sucker for ice cream. And because of rising temperatures, a lot of the foods that we love won't be able to be grown and shipped to us. It might become so hot that you can't sleep, and the air might have so much pollution in it that it makes it hard to breathe. So you're still going to see the impacts of climate change on the local community, even if you aren't forced to move. In Hawaii, there's the example of sea level rise, which I know we mentioned earlier, and king tides, I think someone mentioned, and tracking those. They're only getting bigger. Yeah, and we are starting to see people move as a result of climate change. So I have a question for you guys before we finish on up. How do you want your neighbors to help if you were forced to move? And I don't just mean like climate change, just like in general. If you knew that you couldn't stay in your house, how would you want your neighbors to help you? Who has a truck? Honestly, a U-Haul. Get all the masubis. Yep. And the beers. Okay. Priorities. Yeah, if they could help move furniture, that would be great. I think it's also like the timeline. If you knew that you had to leave in 24 hours versus, can they take stuff that I can't take with me? Yeah, this is a hypothetical scenario. Yeah, I'm sure they could. Oh, Katie, totally relevant. I had to evacuate for the first time because of the Big Island fire. My neighbor made sure that I had my babies loaded into my car for evacuation. They are plants. I'm a millennial. I can't afford a baby. I love that, Katie. Succulents for life. Yeah, these are real questions. Yeah, and thank you guys so much for all of your answers. Feel free to continue dropping them into the chat, but again, I want to leave on a message of hope. This is a very real issue, but there are ways to tackle it, and the first step is just even thinking about it. And now that you know about how much of an issue climate displacement is, and how critical is that we're thinking about issues of climate adaptation, you can use your vote to elect legislators that take the issue of climate change, and especially like how to adapt to climate change impacts seriously. You can talk to council members, call up your local city council members to chat about them, either a phone call or like walk into their office. And then on the mitigation side, because adaptation and mitigation have to go together. We both have to like reduce the emissions that are causing climate change, but also like adapting to the existing emissions. You can reduce your own personal carbon footprint to reduce climate change impacts, like biking or walking. And probably the most importantly is talking about climate change and displacement with your friends and family, and having these really hard conversations about like home and what you do when home won't let you stay, to prepare and think about the future. So that is my presentation. I am actively seeking feedback for it. So here's a QR code. Feel free to scan it on your camera. It sends you to a very quick Google form, and I would super appreciate any feedback that you guys might have. And I'm here to answer any questions.
So everybody see the first slide okay? I hope so. Anyway.
Yep.
Okay.
Yeah, it looks good.
Okay, thank you. So just a little bit about myself. As you heard, I work at the Pacific Tsunami Warning Center, which is an office within the National Weather Service, which is in turn part of NOAA. And we're basically a sort of an emergency management function. We have 2 people on duty at all times, 24 hours a day, just in case there's a significant earthquake that produces a tsunami. The great majority of tsunamis are caused by large earthquakes, or a few other things that can do it, things like volcanoes blowing up, but that can be detected like an earthquake. Landslides are often when they make tsunamis too, but they are also kicked off by large earthquakes, at least the ones that can make a tsunami, a big one like we're going to be talking about today. So we have a staff with a sort of a diverse background. We got folks who are specialists in earthquakes. We have people who are physical oceanographers. Basically, they measure, they're interested in how waves propagate in the ocean. My background actually comes from a seafloor mapping sort of area. So I learned a lot about how to use software tools that make maps. So when I started working at PTWC, that's what I did, is I adapted a lot of that knowledge to addressing tsunami issues. So one thing I figured out is I needed to learn a lot about tsunamis, and the way I did that was make my own figures, basically. So I'll share some of those with you today. So this first, it's going to be showing you a series of animations primarily. And this first one is 120 years worth of earthquakes and when they happen, tsunamis that they created. And what you'll see, we're only up to 1915 now, but back then there wasn't many instrumentation, so they only picked up the big earthquakes. And as the animation progresses forward in time, you may see an illusion of more and more earthquakes, and what you're seeing is more and more detections of earthquakes. So you'll see more and more smaller earthquakes, but the actual rate of like large earthquakes doesn't change that much over time. So now you see a lot of earthquakes in California, for example. But every so often you'll see a sort of purple flash across the screen, and that's indicating, like that one there, that was the 1946 tsunami that came out of the Aleutian Islands that impacted Hawaii quite severely. And then there's another one here that just came out of Kamchatka and so forth. And so the middle 20th century saw several of these big earthquakes. It's the biggest one of all right there was Chile in 1960. There's the Great Alaska earthquake. And then we sort of hit this drought. It goes on for a few decades without big earthquakes and tsunamis. And I shouldn't say without big, there's quite some large ones, but not up in the 9 range until we get almost to 2004. There'll be see one in 2002 from Peru. But what you're seeing right now is it just looks insane with the amount of earthquakes going off, but it's really just, as I said, an increase in detection rate. And increases in telecommunications technology is a big part of that. There was a huge investment in seismology to detect nuclear tests, for example. So there's Peru, and then 2004, there's the big one in the Indian Ocean. And you'll see several others that happened. There's Chile, and then Japan. There's one that came out of Canada. And then I think that's it up until 2020. But I'm also fading in the sources of those earthquakes you'll see forming underneath them. So there's all of the earthquakes in the catalog. And this is the whole entire USGS catalog. And then we'll filter them a little bit. So these are the earthquakes that are known to have made a tsunami. There's quite a few of them, but they're not all destructive. And then it's going to cut away here and show you the ones. These are the ones that are known to cause some kind of damage. It might be just close to where the earthquake was, or it may be damage all the way across the Pacific Ocean. And as you can imagine, the really big ones send the big tsunamis all the way across the Pacific Ocean or any ocean basin. So what we're left with here on the final frame are the plate boundaries. These are the edges of the tectonic plates where two pieces of the Earth's crust move relative to each other. They may move apart, which are shown by sort of the yellow and red lines, or they may collide, which is what you're seeing with the purple lines, or they just slide past each other in the blue-green lines. And all of those big earthquakes that made tsunamis, almost all of them were on the purple lines. That's a particular type of fault. We call it, here it's labeled convergent. We also use the term subduction zone or megathrust. And that's what this next animation is showing you, is a megathrust fault in cross section. So on the left side would be say the Pacific plate going underneath South America, for example. And for hundreds of years, it drags the overriding plate with it, winding it like a spring, you can think of it that way. And then after several hundred years, the 100 years worth of energy is released all at once in a matter of minutes. And it moves so fast, the ocean over it can't get out of the way. So it shoves the water away, and then it sets up these oscillations that can last for hours to days. And that's the tsunami. A tsunami is not a single wave, it's a series of waves, as you'll see in the upcoming animations. So like I said, I'm mostly going to be talking about output from a forecast model. And it's basically, that's a computer program that uses mathematical equations to predict the behavior of, in this case, tsunami waves as they propagate through the ocean. And we can base it on things we know about the earthquake. And we can learn a lot about the earthquake fairly quickly. We need to know where it is. That's critically important. Is it close to the ocean? Is it under the seafloor? Or is it under the land? If it's under the land, it's not a problem for tsunamis. If it's deep within the earth, it's generally not a problem at all for anybody. It's just interesting, no matter how big it is. But if it's under the seafloor and it's close to the seafloor, if it's shallow within the earth, and if it's large, if it has a high magnitude, say magnitude 8 or larger, it has the potential to shove the water out of the way, like I showed you in the last slide. But it depends whether or not you have one of these megathrust earthquakes, for example. Some earthquakes move sideways, some of them, when they move sideways, they don't generate big waves because they don't push the water sideways unless they make a landslide or something like that. But these animations are pretty complex graphics. They show lots of information at once. They show where the waves are, where they're happening, and you see them propagate through the oceans. You can also see them bending and bouncing, in other words, refracting and reflecting. And that is a function of water depth. So I kind of skipped a bullet point here about the knowledge of the ocean. The big one is how deep the water is. The deeper it is, the faster it is. The shallower it is, the slower it is. And it behaves just like an optical lens. And so it'll bend the water around, bend the waves around when it passes through slower or shallower water. You see how fast they move. They're moving really fast. In deep water, they move the same speed as jet aircraft, around 500 miles an hour in the open ocean. You can also see how far apart the waves are. In other words, frequency or wavelength. And this varies based on the size of the earthquake and the geometry of the earthquake. I'll show you some examples of that in a minute. And then this animation also shows you how big the waves are. So on the open ocean, you can see they're colored by how tall they are. And then the colored dots along the coastlines are there to show you what happens when they hit the coast. So something happens, tsunamis change their character when they enter shallow water. They slow down, they pile up, and then they become quite a bit larger when they come ashore. So a tsunami out in the open ocean, even though if it's a huge wave, and I'm talking about huge, it's hundreds of miles from wave crest to wave crest. But on the open ocean, it'll only be a few feet tall. But when it comes ashore, that reverses, and the waves get closer and closer together, but they also get taller and taller. And finally, the other important piece of information this can hopefully guide you on is how long the hazard lasts. Tsunamis, once they started, they last for a finite amount of time and then they decay away. So when we issue warnings, we issue cancellations in part based on the forecast like this, but also in large part on the observations. We have sea level gauges around the world. Most of them are on coastlines, but we also have some that are on the seafloor. they're co-located with the buoys you heard about. The buoy's a radio antenna that sends the data to us. So this is an actual forecast graphical output as you would see within the PTWC. If we had a large earthquake in Japan, and this is showing you something similar to what happened 10 years ago in Japan, this is the kind of model output you would see. We don't, you know, the operators or the analysts don't see the discrete waves like I just showed you, but it shows you a summation. So the map on the left is, you can think of that as showing you every node on the surface of the ocean, how much it was lifted up by that tsunami over a particular period of time. In this case, I think it's 36 hours. And what you see is that they're not big everywhere. They're big in a more or less a line or a beam that goes through the middle of the ocean. And that's because tsunamis, the earthquakes are not point sources. They're not pebbles being dropped into ponds. They're line sources. You think of a log rolling into a pond and you have a set of parallel waves off the middle of that log, and they're quite large, but on the ends, they're quite small and they decay away rather rapidly. So there's, in this case, we're simulating a fault with a particular length, in this case about, I think it's about 300 miles long off of the coast of Japan. And this was a magnitude 8.8 in this simulation. We now know it was quite a bit larger than that. But the distribution of energy would be similar. It shows you this beam that passed all the way across the Pacific Ocean, impacted South America, and this was observed as well. There's also this beam that breaks off because there's a submarine ridge here that peels it off, and it goes and hits North America, and Northern California and Oregon were impacted as well. The figure on the right shows you the coastal impacts, or a sort of a quick and dirty rule of thumb sort of coastal impact using something called a Green's law. It takes a point from this deep water grid and projects it on land to see what it would be. And this is basically kind of tells you, is it dangerous or not? We wouldn't use this to tell you to a fraction of an inch how big the wave is, but it's going to tell you whether is it a 10-foot wave or a 1-foot wave. It's that sort of scale that it's trying to convey to us. And you can see in Japan, it has all these hot colors. Of course, there's large waves here. There's actually hot colors here in Hawaii, and that was true from that event. We had significant impacts in Hawaii, nothing like Japan, but they were quite large. And again, you see Northern California, Oregon as well, but also in Chile, they had over 6-foot waves down in Chile, if I recall correctly. And a piece of information you see on here is are these contour lines, and those are time. The solid lines are 1-hour increments, and the speed of as I said, the speed of the waves is based on the depth of the ocean. So in the open ocean where it's quite deep, they move quite fast. And you can see that it reaches Hawaii from Japan between 7 and 8 hours. And just to drive that point home a little bit, here's an animation just to show you how fast these things move. So this is shows you an Alaska earthquake. It gets here in 5 hours. That's how much time we have to prepare for it once we know an earthquake has happened. But earthquakes also happened in Hawaii, and this is the 1975 Kalapana earthquake and its tsunami, and shows you that it goes all the way through the state in under an hour. It reaches Honolulu in just a little over 45 minutes. On the Big Island itself, of course, it's if you're right next to it, it all comes ashore in a matter of a few minutes. So this is a kind of our worst case scenario, and why we spend so much time on education too, because your only hope to survive something like this is that the earthquake itself is going to shake the ground and you're going to feel it. If you're within 2 minutes of travel time of the tsunami wave, there's a good chance you also felt the earthquake, and that is your tsunami siren, is the quake itself. So the next I'm going to show you is tsunamis that happened earlier this year. This is from March, and this is something pretty unusual. We had 3 tsunamis in a single day. So remember I mentioned subduction zones. This feature here north of New Zealand is the Tonga Kermadec subduction zone or trench. And so this New Zealand, the Kermadec Islands are in the middle, the Tonga Islands and Samoa are up at the top. So start that to run. So first we'll show you unperturbed sea level at the coastlines, all the dots are blue. And the first tsunami kicks off from the North Island of New Zealand. It was a magnitude 7.3. And there's the second one, that was from a magnitude 7.4 in the Kermadec Islands. And then there's followed by a much larger one of a magnitude 8.1. That 8.1 earthquake's about the size of the one we had in the Alaska Peninsula last Wednesday. And what you're seeing now is all three tsunamis propagating through the southern Pacific Ocean. The dots are changing colors to show you the impacts of the tsunamis as the model would predict it. And what's kind of showing you is the worst, of course, is right close to where the earthquake was, right here in the Kermadec Islands. Fortunately, those are nearly uninhabited. This is basically a weather station out there. It's a military base with a few people on it. Look, actual inhabited islands in New Zealand and Tonga and further away, although they observed tsunamis, they didn't observe a damaging one. So this is not actually, despite my title, this is not a damaging tsunami. This is an interesting tsunami. And there's the energy map that I showed you from the previous slide, showing you sort of the ray pattern that came off of it's dominated by the largest earthquake and its tsunami. And then we're going to look at when that truly was damaging. This is 2004 in the Indian Ocean, and from the Sumatra Andaman earthquake, which was a magnitude 9.0. And it's putting off huge, huge waves. And you also see that it has huge wavelengths because the fault was really, really long. It was about 1,000 miles long. And so when the longer your fault, the length of your fault that moves, the longer the period between your waves and the larger the waves, generally speaking. So these are huge tsunami waves as they move through the Indian Ocean. And of course, they were very devastating in the near field in northern Sumatra and the Andaman Islands, also in Sri Lanka and in the Maldive Islands, but also all the way over to Somalia. It was damaging. Now, back in 2004, the US tsunami program was focused exclusively on the Pacific Ocean. It's in our name, the Pacific Tsunami Warning Center. But as a result of this event, the United States chose to enhance its tsunami program, and it doubled the staff of the two warning centers. They expanded the area that they covered for a while to the Indian Ocean until they got their own system up and running, and the Caribbean Sea. And one of the people they hired was me. So I was actually brought in, this is 16 years ago now. I was hired a year after this event. So 15 years ago, I started working on tsunamis. And so another very large one is, this is the Japan 2011 again. Like I said, it was 10 years ago this year in March. So this one, now we're further, it's a larger ocean, so the waves look smaller, but they actually are higher frequency waves because this was a shorter length of fault. It moved a lot further. The fault itself moved much further, but it had a shorter length of fault. So that produced these much finer, waves. These very that sort of lacy look you see compared to the last one is because of these high frequency waves. And again, you see that the impact was very awful in Japan. It was pretty bad in Hawaii. You see it's pretty intense up in the Northern California coast and Oregon, as I pointed out earlier. And you see, but throughout the Pacific Ocean, lots of areas are showing up in these pinks and red colors that indicate that they're over 3 feet or over 1 meter in height. And that goes for South America as well. And what you can probably see now, if you look carefully, I hope it's making it through the transmission here, is reflected waves coming off of South America. And these were even observed in Hawaii a day and a half later. They're about to reopen Hanauma Bay, and the lifeguards started to see the bay go up and down again long after the first waves had passed. So they closed Hanauma Bay for another day. And then finally, here's the energy map. We call this the summary of the maximum wave heights in this 36-hour period. So here's what we actually really, really care about. All that information from the tsunami forecasting, from the earthquake, from the sea level changes that we're measuring is to issue messages. The name warning is in our name, Tsunami Warning Center. And it's a little unfortunate because that means everything we publish has the word warning in it, even when it's not a warning level event. And warning in emergency management means specifically an evacuation recommendation. So when if we feel that it's very likely that a particular piece of coastline will be flooded by the ocean due to a tsunami, we put that piece of coastline in a tsunami warning status. The cutoff, it says run up, that's how high the water is when it comes on land. 3 feet or 1 meter is the criterion. Sort of a low-level warning is something called an advisory. And this, you'll hear this referred to as a marine threat. And this is where they tell you to stop swimming, no surfing, get out of the water, secure small boats. But you don't have to evacuate anything on land. Nobody has to close a school or a business or anything like that. There's no recommendation for people to leave their homes, but they want people to be off the beach. So this is still requires action from the public, but it's not nearly as bad as a warning. And then watch is what we actually had here in Hawaii last Wednesday. This was for a couple of hours after a significant earthquake in the Alaska Peninsula, which we now know is a 8.2 magnitude earthquake. While we were analyzing it and trying to figure out if it was a tsunami threat or not, we put the state of Hawaii into a watch. That does not blow any sirens. That does not require anyone to do anything yet, except for professional emergency managers. So the folks in the Hawaii Emergency Management Agency out in Diamond Head, they increased their staffing. They prepared for the worst while we were doing our analysis. And it turned out, thankfully, this earthquake was actually quite deep. And so even though it was an 8.2, which would make a significant tsunami if it had been a shallow earthquake, as a deeper earthquake, it did not. It made a measurable tsunami in Alaska, but it did not cause any damage, thankfully. And the most common product we issue is something called an information statement. You'll see this from us probably a couple of times a month. And that means that there's been an earthquake that people have likely felt and they're concerned about, but it's not going to have any tsunami hazard associated with it. And this is important information too. It tells emergency managers that to worry about the earthquake, they don't have to prepare for a tsunami. It tells folks in the public the same thing, that yes, there's an earthquake, it may even be a bad earthquake, but the tsunami is not something you have to worry about. But we issue these for even really small ones here in Hawaii, because magnitude 4 in Hawaii will prompt us to put one of these out, because we have a lot of visitors here who don't live in earthquake-prone parts of the country. Folks on the Big Island know what magnitude 4 is not dangerous, but someone was in their first day there, they might not be so confident in that. So if we go back to Japan, we put this all together. What I'm going to show you graphically are the watches and warnings and advisories that were, that were issued over, in this case, a 48-hour period following the earthquake and its tsunami. So there's the earthquake, and those boxes that you see lighting up are the geographic regions putting these different statuses. And you'll see they change colors. Some of the ones that were in watches turned into warnings, and you will see warnings that are downgraded into advisories. And eventually you'll see all these boxes canceled as the danger, as far as the warning centers can tell, has passed. Within the limits of our instrumentation and our forecasting ability, we will figure out that that they're no longer necessary. So you see Micronesia's, the boxes are disappearing. They're still up in French Polynesia, but they'll go away pretty soon too. Meanwhile, Japan is still in a warning status. They are still experiencing lots of aftershocks. There's still potential tsunami hazards there. The Aleutian Islands are lit up as in an advisory status. And now almost everything is dropped except for, looks like California, Oregon, and the Aleutians. And I should have pointed out at the beginning of the talk, the United States actually has 2 tsunami warning centers. The one we have here takes care of international stuff and basically US territories that are islands, whether it's the state of Hawaii, Guam, Samoa, Puerto Rico, Virgin Islands, and the Northern Mariana Islands. Those are our domestic sides. And then internationally, it's most of the countries around the Pacific and within the Caribbean Sea. The center up in Alaska takes care of basically North America and north of Mexico. They take care of the US mainland, they take care of Alaska, they take care of Canada. And so here's the energy map fading in one last time, showing you sort of on a global scale, a global projection, how it wraps around the Earth. So this is my final slide of the formal presentation. I have more animations if people want to see them. But this is to, if you like this kind of stuff, if you think it'll be useful either for teaching or your own edification, whatever, we have a YouTube channel where I've put many of these, there's dozens of these out that you can use to your heart's content. And as we heard in the last talk, the Science on a Sphere project, I've created lots of these in Science on a Sphere format too, which you can either, if you get a chance someday to go see one in person, it's a wonderful exhibit. But before then, you can use this SOS Explorer app on your phone. You can download this and have an interactive sphere on a phone or a tablet. And there's even interactive spheres on the website itself. And with that, I'll be happy to take questions.